Any more submissions for homework 6? Homework 6? All right. Your next homework assignment is dealing with evaporation, which we're going to be starting with today. And that assignment's due on Thursday of next week. Also looking into the future, stage 3 of the project is due on October 31st. That's what we discussed last time, and if you want to review the discussion of that process, of course the lecture recording is posted online. And the way that you're going to submit that is just uploading the maps to MU Online. So any schedule or announcement questions before we move forward?
For the exam, is it everything up to the exam, or is there a certain point?
It's everything up to the exam. Yeah. Right.
Do you have a format
For the exam?
Yeah.
Paper?
All right.
Rather than computer-based?
Yeah.
No, I don't have any format in mind. I haven't even started thinking about writing it yet. What we're going to be talking about today is evapotranspiration, and the text makes the point that the magnitude of evapotranspiration is oftentimes very small for a watershed, and I'm going to make the point that it's extremely difficult to model evapotranspiration. And so this aspect of the hydrologic process has the distinction of both being maybe the least significant and the hardest to measure. But that varies depending on where you are. Some watersheds, evapotranspiration is a very small part of the overall water balance. In other watersheds, it's a huge component. And I thought the way that I'd introduce the topic of evapotranspiration to you is to, after we look at some just preliminary videos here, tell you about a research project I did this past summer for the West Virginia Department of Environmental Protection. So we always got to start off with some YouTube videos, though, so let's go ahead and do that. Yeah, we're going to watch water evaporate. That's exactly how interesting today's lecture is. Wait for it. All right. Yeah, it's evaporated. Twice is all you get today. Let's take a look at another one of these videos here. A lead and frost effect. This one's kind of interesting at water because liquid bouncing right off of the pan. The water is evaporating so quickly that the water vapor on the bottom part of the droplet is flowing into the liquid is suspended. So, oops, that was not what I wanted to do. So, pour it in a really hot pan, it's instantly vaporizing, and so that's why water bounces around and and finally, water evaporating instantly on a very cold day.
Sydney needed some financial guidance so she could take her
Get 2
dream
for
to the
free.
next
The third,
level.
you've got to watch a commercial.
What are you doing, Sam?
So what I've done is boiled
Maybe
water in the
30
kettle.
Celsius,
So it's
very
boiling
cold.
water. We're going to pour it in here and then throw it in the air and it's going to evaporate. Ready?
Oh, wow! That's amazing.
Perspectives on
Usually if it was warm out it would go
evaporation.
plunk in the snow. But
What we are generally more
That's so
interested
cool.
with, I guess, three.
it's like
three
instant
is
fog.
on.
I know! That's crazy.
Northwest Territory. It's a province of Canada. All right. So that's at one spectrum of evaporation, just looking at liquid evaporating because of a really high heat being applied to it, or a very large differential between the liquid temperature and the air temperature. But at the other end of the spectrum is long-term evaporation, and that's a project that the West Virginia Department of Environmental Protection asked me to take a look at this past summer. They have a lot of watersheds in the state that they need to develop an estimate of how much water could be withdrawn out of a watershed, because there are certain industries that would like to locate in West Virginia to take advantage of one of its natural resources, and that is the availability of water. And so there are coal processing facilities, chemical plants, gas processing facilities that need a constant, reliable supply of water, and we have that here in West Virginia. But the DEP wants to make certain that they don't bring a business into the state and then give them the wrong idea of how much water they can extract. And you know, over the long term, there's going to be some years that are very wet and there's plenty of water, and other years that are very dry. And so the DEP wants to have an idea of what's the safe amount that can be relied upon to always be there for the industry. And that's the project that I took a look at, is analyzing some flow data over time and trying to come up with a model to predict in the future how much water might be there. And so I did this study as a pilot study to develop the methods that should be used for the Greenbrier watershed. And Huck 8, which it says at the top there, it's kind of a classification system that's used to describe the very large watersheds within a state, or sometimes these watershed boundaries cross states. And you can see here that the Greenbrier Huck 8 watershed has an area of 1,650 square miles, and so it's one of the largest in the state. There are about 32, I think there's 32 Huck 8 watersheds inside of West Virginia. And this is one of the simplest because, number one, it doesn't have any rivers flowing into it. You know, sometimes, for example, the outflow of this watershed goes into another Huck 8 watershed, but this one doesn't have any rivers flowing into it. Any flow that's going on in this watershed is a result of just precipitation that's fallen inside of it. The other thing that made it a good place to start for a pilot study is that there's not very much agricultural going on inside of the watershed. It's mostly just raw forest, and whatever agriculture is occurring isn't consuming a lot of water. It's not like in some places, you know, Nebraska or Iowa, where they've drilled down into the aquifer and are tapping groundwater resources to irrigate crops. It's not like that here at all. And there are characterizations of large volume water users, like if there were any sort of mines in the area that are using water, or towns that have water treatment plants. And the other thing is that there is a very limited large volume user. And so basically this is a wild watershed that just doesn't have very much human impact on it yet. And so the advantage of starting with a watershed like that is that it eliminated variability and would allow me to try and predict the runoff as a function of the evaporation and the rainfall. If we look at just in general what's going to account for runoff out of a watershed like this, this is the runoff model conceptually that I came up with for at the Huck 8 level, where the water is going to and where it's coming from. And you can think of it as a mass balance. If you think about a watershed as, you know, a container, then what we're saying in this runoff model is that the flow can come in to a watershed, and so Q in, I was talking about how there may be some watersheds with an upstream watershed that's contributing flow already channelized. This particular watershed didn't have any flow in, but other watersheds do. PR is precipitation, and so, you know, there's going to be rainfall coming into the watershed, and we've talked about precipitation already this semester and its temporal and spatial variability. Over a watershed that's 1,650 square miles, then it's very challenging to try and say how much precipitation there was just by using the rain gauge at 1 or 2 points. And in this watershed area, there are 2 gauges with data that goes back really far. And there are a handful of others that would have 10 or 15 years of data here or there. And so the precipitation data is a real challenge for a watershed that's this large. Because when it rains, if you look at the correlation between the 2 gauges, I think there's an airport up here and then another gauge down here that's pretty reliable. Sometimes it would be raining on the same day at both gauges, and sometimes it wouldn't be raining the same day. And so both temporal and spatial variability within the precipitation aspect of the model was a significant factor. So precipitation. Evaporation is the process that we're going to be focusing on, and evapotranspiration, to be more specific. Evaporation would be the loss of water from a free surface of water like a puddle or a stream or a lake. Transpiration is the process of plants giving up moisture, and so combined together they're often modeled jointly, evapotranspiration. And one of the main things that DP was interested in is coming up with some way to model evapotranspiration. Of all of the things here, we can directly measure, or we can make good assumptions about everything except for evapotranspiration. It's by far the most complicated, and it's sort of been elusive. DEP has for a lot of years been trying to come up with some way to model evapotranspiration. All right, GR is groundwater recharge. Over the short term, remember when we speak about infiltration, we know that during a storm event, infiltration has a declining rate. And we've looked at this chart both in terms of the Horton model and in terms of green amped, that over time the infiltration rate is decreasing as a storm begins. But when you look at what's happening in a watershed over an annual basis, then groundwater recharge, which is the effective infiltration, is steady. Because think about it. Here is in the watershed. There's let's say this represents the ground level, and then here's the water table underground. And so this is the saturated zone, and then here's the zone of aeration. What would happen if groundwater recharge wasn't steady over the long term? Like if there was a net positive recharge or a net negative groundwater recharge? What would happen to the water table level if there's, over time, positive groundwater recharge? I mean, year to year to year. Yeah, if there was positive recharge, for a net positive recharge for multiple years, then the water table would be going higher and higher and higher and higher, and eventually all of the soil would be fully saturated. And we know that that's not true. And so groundwater recharge over the long term, you can assume, is steady. Here in West Virginia, that's a fair assumption. There are places like El Paso, Texas, where that's a horrible assumption. Or in the United Arab Emirates, where they're completely exhausting all of their groundwater resources. In the western United States, in Idaho, a lot of agricultural regions in the western United States have had a net negative groundwater recharge for a number of years. So they're consuming groundwater. But in the case of this watershed, it was fair to assume that over the very long term, groundwater recharge is steady. And the same thing's true of surface water storage recharge. And so this particular watershed has very limited surface water. The open water area is 0.5 square miles. So there's not a lot in the way of lakes. In fact, there's no lakes of any consequence. I think that the majority of that open water area is just stream area. And because there's so little open water area, for that reason, it would be easy to assume that surface water storage recharge is 0, because if there's no area, then there's really no surface water storage that needs to be kept track of. But then for the same reason, over the long term, if there was a negative surface water storage, then we'll represent this as a pond here. Here's a little pond. If it was positive, then the ponds would be filling and overflowing. If it was negative, then they'd be drying up. And so the short term, it'll definitely fluctuate in the short term. And so during a storm event, for example, the groundwater the saturated zone will get deeper, and then over the dry period, the saturated zone will get lower. But over the very long term, it's constant, both delta S and the GR, groundwater recharge. And as I mentioned already, large quantity users are negligible. There's just a couple of small towns inside of the watershed that aren't using very much. If you look at the water extraction from the rivers, it's less than 1% of the average flows that are there. And so the water that's extracted for industrial uses or for potable water production is just a tiny fraction of what's available there, which is why some industries sort of are rubbing their hands together and think about all that water that they could use up, because there's plenty there at the moment. Agricultural water consumption also zero. And so simplified, for this watershed there was no flow rate in, large quantity users are neglected, agricultural waters users are neglected, and then over the long term, remember that we can cancel out groundwater recharge and surface storage change. And so really what we're saying is that outflow is equal to precipitation minus evaporation. And so that's the model for this watershed. There's a watershed, and what we'd expect is that over the very long term, we should be able to predict how much water is going to come out of the watershed simply by how much rain there was and how much evaporated. And that's taking a very complicated runoff model and making it very simple. But that's only valid over the long term. On a day-to-day basis, this model wouldn't be very accurate because there's a lot of individual variability that's happening on a 1 or 2 day basis. You know, there may be one day where it was very dry. There would be, for example, a day where there's no precipitation. And so from the model you'd say, well, there can't be any outflow if there's no precipitation, but then the rivers are still running. And so the model really only works on a month-by-month basis or on an annual basis. It doesn't work over the short term. What I did in this project was I used a couple of different data sources in order to define the watershed boundary, for example, online. I don't know how many of these websites are going right now, but over the summer anyways, you could get the Hecate watershed boundaries online, and I also compared those watershed boundaries that were pre-delineated to the delineation model I've shown to you before, where you can just sort of click I just found an 8 gigabyte memory card. It's been through the wash a couple times, I'm sure, so who knows if it still works. I thought for a second it was a quarter. All right. The other thing is that luckily, another reason why this was a good place to start for a watershed, for a pilot study, is that there is a stream gauge right at the outlet. And that's perfect because remember, what I want to do is I'm going to try and develop a way for predicting outflow. And the only way to know if you're accurate at predicting outflow in the future is to look at in the past. How does is your model able to predict what happened in the past? And so you have to have an answer. If you're going to make a guess, you can only know if your method of guessing is accurate by putting in old data into the model and having the model predict what happened in the past. And thankfully, you can see that there is a stream gauge at Greenbrier River at Hilldale, West Virginia. And it has, and you probably can't see this, it has daily statistics going from 1936 to the present. So there's a nice long history of stream gauge data there on a daily basis. For precipitation, you've already looked at the PRISM website, I think, University of Oregon, or was it Oregon State? I think it's Oregon State. And it's gridded precipitation data, because remember I mentioned that in this watershed there's only a couple of rain gauge stations, and so rather than me trying to extrapolate those rain gauge stations, I used what's considered the definitive spatial representation of precipitation data. The other thing, now we're getting into the evaporation a little bit here. The other thing that I needed to do was be able to predict how much evaporation was happening inside of the watershed. And to do that, luckily, in Bluefield, West Virginia, there is a pretty good radiation gauge. It's got data going back to 1999, and that doesn't seem like a lot compared to the runoff data going back into the 30s, but I felt fortunate to have the solar radiation data just outside of the watershed. And so you can see here's Bluefield, West Virginia, and the solar radiation wasn't inside of the watershed, but solar radiation doesn't vary as much as precipitation does. Remember, if it would be really a bad practice to try and predict what happened in terms of precipitation in here with a rain gauge that far away, but it's not so bad to estimate how much sunshine there is based on a radiometer that far away from a watershed, because solar radiation doesn't vary spatially as much as precipitation does. You know, when it's the summertime and there's a lot of solar radiation, there's going to be a lot of solar radiation in Bluefield just like there is inside of the watershed. And the only variation for that is days where it's cloudy in one spot but not in another. But remember, this model is meant to predict what's happening over the long term, you know, seasonally or annually, and so any variation should average out over the long term. There is gridded solar radiation data available where they've done the same thing for solar radiation as they have for precipitation, meaning they've connected all of the stations across the country and then come up with a point-by-point representation of how intense the sun is from spot to spot, but I didn't get to the point of implementing that gridded solar radiation data. You know, if the DEP wants to move forward with applying this model into other watersheds, then I might try that in the future, but didn't do it yet. For the evaporation model, you also have to know things like relative humidity, temperature. It's helpful to know the temperature of the air and the soil separately, and a lot of that data is available on the National Climatic Data Center website. So this is what the this is what the precipitation data looks like. These are the gridded points that you can get from PRISM, and I think it's a 4-kilometer spaced grid, and so each one of these dots is 4 kilometers away. And the nice thing about this data is that it's accurate, and it takes any guesswork out of the process for the modeler. Like, you just say, well, this is the standard for precipitation data. I'm going to build a model based on the standard, and so it's repeatable. You could apply this method here or in any other watershed, and it takes the guesswork out of it because PRISM is a product that's available for the entire continental United States. But the disadvantage of this is that I needed the help of a GIS specialist, and maybe some of you have taken classes from Jamie Wolf before. He's sometimes works as an adjunct, but his main job is to work for one of the research institutes that's in the college. It's called CEGIS, the Center for Environmental and Applied Geological Studies, something like that. Every day, the data set is 20 megabytes for the entire US. And so the process that he had to go through was, first of all, you get a map of the whole United States on a day-by-day basis. How much precipitation was there on June 3rd, 1989? And so there will be a map of the US that every 4 kilometers it tells you how much precipitation there was. And so he had to, first of all, clip out just the data that we were interested in this watershed area, and then he had to do it for about 10,000 different files, you know, starting 365 of these 20 megabyte files, and he had to do it from our period of study was from 1986 to the present. So it was a lot of data crunching. You know, he had a pretty fast computer, and he had to custom write the script that would execute it, and he started the script and walked away and came back 6 hours later, and it was finally done processing. But that's a lot faster than the alternative would have been, for sure. By the way, feel free to interject with any questions if you have some. Yeah.
Those points on there, what they significant? Or I see that they were,
Those are little airports there. You can see there's an airport, a couple of airports up here in the north part of it, airport here. But, I mean, they're not big airports. Here's some other characteristics of the watershed. Sometimes you might be interested in the curve number. It's a very low curve number. extraordinarily low. But the other thing that that's notable about this watershed is how high the average slope is, 18.8%. And that's talking about over the entire watershed area, the average slope of the land is 18%. And slopes like that are kind of unique to West Virginia. I mean, people are a little bit shocked when I'm showing hydrologic models that I've built at how high the overland slopes are, because you know, we're uniquely mountainous for the entire state being so steep. So I did build a HEC 8. You get HUC and HEC confused, but HEC stands for Hydrologic Engineering Center. A HEC 1 model to try and compare how much water was coming out, the outflow for the watershed, to the rainfall that's coming in. But ultimately it wasn't very useful, because a HEC 1 watershed is used to predict flow in the short term, but this project was more about predicting what's coming out of watershed on a seasonal and an annual basis. And so before I show you the spreadsheet of evaporation, because really what this is all about is building an accurate evaporation model, I'll show you some of the questions that can be answered even before you build an evaporation model, and then we'll talk about what kind of questions can't be answered without building an evaporation model. So why to go to the trouble? This will sort of illustrate it. This is showing where the watershed exits, and so this is the Greenbrier River exiting the Greenbrier watershed. And just by looking at the stream flow data, that record of data that went from 1936 until the present, you can look at questions like, on average, how much runoff is there at the location during the month of July? Because remember, what the DEP is trying to figure out is how much can they let people withdraw from the river. If they take out too much water from the river, then the risk is they may not leave enough for the fish, or the businesses may not leave enough for the communities that are relying on this as a water supply. And so they want to understand how much water is there, and over the long term, how much water is there. So just the easiest question you can ask is, what's the average availability for the month of July? And so just by looking at the stream gauge data, now even though the stream gauge data goes from 1936 to the present, we chose a period of analysis from January 86 to the present. And the reason why is that it was from January 86 to the present that we were able to model evaporation. So during that period of study, you can find the average runoff depth, and you can convert the runoff volume to a runoff depth by taking into account the area of the watershed. Now you already know that precipitation amounts can be expressed as a depth. 1 inch of rainfall, for example, is a way of representing precipitation amount. But you can also express runoff as a depth. And I think actually we've had questions like that before, where you had to convert it into a depth by dividing by the area. An equivalent flow rate would be 677 CFS. And so, for example, if you took all of the water that was in the river, you could take 677 CFS during the average July. But I've shown the normal distribution here to make a point. What we're talking about is the average amount. And so that would mean 50% of the time, 50% of the Julys, you may have more than 677, and the other 50% of the time in July, you're going to have less than 677. And so if you told a company that, well, on average, we have 677 CFS available in July, and if they built their factory to consume that much water, what that means is that half the time they're not going to be able to operate their factory, because half the time there's not that much water available. And so you can't just go by the averages. That's maybe a little bit unconservative. Now let's take it the other way. Now what if you were saying, Well, we have to preserve some flow for habitat. So if you have to assume preserving 500 CFS for habitat, then how much water could be withdrawn from the worst March in record? And so now by worst, what we mean is that almost all of the time is going to be better than that. It's just what we haven't observed from 86 to the present that's the risk that we're worrying about. And so over the course of, how many years is it from 86 to the present? Like 26, 27 years? So, you know, what we haven't seen is about the 4% risk. So you can see that from March, the minimum that we saw during that period of record was 1,091. So subtract 500 from that, that's 591 that could be withdrawn. So these are the types of questions that can be answered even without looking at the evaporation. Is just based on the historical data, how much water has been there in the past. But actually starting to account for the evaporation makes things a little bit more flexible, because you can extrapolate into the future. You know, what haven't we seen? And once you start to model the evaporation, then you can address questions like what we haven't seen before. Now, we've already talked about how the overall model simplifies down to runoff as precipitation minus evaporation. And so both of these factors, precipitation and evaporation, are expressed in the runoff in the historical data. Now, the stream gauge that's at the outlet of the watershed, it is a reflection of two things. It's a reflection of how much precipitation there was and how much evaporation there was. You know, the stream gauge is sort of automatically accounting for both of them, because the runoff is the difference between the two. So in an October month, what if we had more than average precipitation and below average evaporation? And now, in order to answer a question like that, we have to separate the precipitation and the evaporation. We can't just have them lumped together in the one component of runoff. And so if we had above average precipitation and below average evaporation, then we're going to have a lot more water available than usual. And so this is the type of question that now you can answer if you separate the evaporation and the precipitation. Now, I'll show you how I got to an estimate of evaporation in just a minute, but basically you can do the difference between the two, the precipitation and the evaporation, and find out how much runoff is available to be used by the company. Or maybe you could ask the question, what if it was April and you got 4 inches of precipitation, and we calculate the evaporation by the evaporation model. Now, for an average April, I know what's the typical temperature profile, I know what's the typical relative humidity, what's the typical solar radiation, and so you can go through each one of the parameters that dictates evaporation. And this is I'll go through all of the equations that are involved in calculating evapotranspiration. And the first thing to mention is that PET stands for potential evapotranspiration. And that's the first caveat of modeling this, is that the model only predicts how much could evapotranspirate, not how much did evapotranspirate, because you can only evaporate as much water as is actually there. And if it's a very, very dry month last month, then this month we may not have very much evapotranspiration, simply because there isn't the water available to be lost. If it's already all dried out, then you're not going to have additional evapotranspiration. And so PET, potential evapotranspiration, is a way of characterizing how much evapotranspiration could occur based on the radiation, based on humidity, temperature, and so on. And so, first of all, the delta here, that is the slope of the temperature, relative humidity curve, and it's a function of temperature, and you put in the temperature of the air into this this calculation. The psychometric constant gamma is a function of the atmospheric pressure and the specific heat. Alpha is a calculation of that just incorporates the temperature. And we'll take a look at the spreadsheet that I used to calculate each of these quantities. Basically, they all depend on the relative humidity and the temperature of the air and the radiation. Now, the thing that I've just assumed in the spreadsheet is either constant or is related to the air temperature. There's long-wave radiation and short-wave radiation, and we've had questions about that on a previous quiz. The long-wave radiation is the radiation that is reflected from the Earth's surface back out in towards space. And so when we're measuring the radiation S sub n, that is going to be the solar radiation, and that is the incoming shortwave radiation. But then the long-wave radiation you can estimate as a function of the air temperature. And then the G is how much energy is being lost by the ground. And so it's also a function of temperature, but this formula here for measuring how much radiation is being emitted by the ground, you can see it's a function of the temperature of the day before and the day after. And so you basically, in calculating how much heat is lost by the ground, you're trying to compare how much the temperature is changing from day to day. If it was very cold yesterday and it's very warm tomorrow, then that means that the soil is warming up. But if it's warm yesterday and cold tomorrow, that means that the soil is cooling, and so it's giving up more energy. So the type of question that can be answered once you actually have a model of evaporation up and running is, for a typical April month, where you have this profile of all the characteristics of what allows you to predict evaporation, then if there was precipitation of 4 inches, how much runoff would there be? And there's this process of looking at comparing how much potential evaporation there was to actual evaporation, because remember, PET just stands for potential evaporation. And I looked at all the historical data and came up with, on a month-by-month basis, the ratio between the actual evaporation and the potential evaporation. It came up with these factors. And then if you multiply the potential that can be calculated by this series of formulas by the factor, so for April, for example, if we took a typical April, then the potential evaporation would be 4.58 inches, but then we have to multiply it by 0.263, because in April, only 26.3% of the potential evaporation actually evaporates on a historical average basis. And there are some occasions where the evaporation is greater than the precipitation, and so in that case you limit the evaporation of the precipitation. You don't say that it's actually going to evaporate more than it precipitates on a long-term basis. And so you go through this process and you can calculate how much runoff there was. And so how good is the model at predicting something like that? Just to jump right to the finish, this is how good the model was. You can see that if you fit the equation through 0, which is what it ought to do. I didn't force it to 0 through, in Excel you can make your equation go through 0 artificially. These factors were selected such that the equation had a slope of 1 and went through 0. The slope of 1 means that it doesn't overpredict or underpredict the runoff. And so here is how much runoff would be predicted by the model, and here is how much runoff was there actually based on the stream gauge data. And so an R² of 0.74 is really good when it comes to a long-term average for predicting runoff out of a watershed. Each one of those dots represents a different month from '86 to the present. There are models that have been published in the literature that have an R² of about 0.6. And there's lots of variation here that the model doesn't take into account. The reason why that isn't a straight line is that there are some months where there isn't any precipitation, but there's still going to be runoff because of base flow, because of groundwater moving out of a watershed and providing the moisture. Other variants, so like I just mentioned, the change in storage groundwater. Some of the other variants is because in the evaporation model, which I'll open up the spreadsheet in a minute, the values that I used are just sort of typical values rather than actually measured on a daily basis. Sometimes it'll throw things off if there's a really big storm at the end of the month. So if you have a precipitation event in April, but then you don't see the runoff from that event until May because the storm was on the last day of the month, then that can throw things off a little bit as well. Snow is kind of tricky because it melts more slowly, and so if it precipitates during one month but then the snow doesn't melt until the next month, then that complicates things a little bit. Then there's also spatial variation effects in rainfall, temperature, and so on. So let me open up the spreadsheet and just show it to you. This is evaporation is probably the most complicated thing I've ever had to model before. It took me a solid month to make this one spreadsheet, and it doesn't look that complicated when you're finally done with it, but I had to learn a lot along the way and find ways to get the data. So what this model does is requires you to go get measured values. Some of the time I've made an assumption on values that are difficult to gather the data for in the project area, and then the calculated values that come out of the equation you can see have a column that's in blue there. Alpha is a calibration constant, and in the equation that I showed you for potential evapotranspiration, it starts with an alpha, which is just a scale-up factor that says how much potential evapotranspiration you should see. Roughly speaking, this part of the equation is relating how much energy is available, and this part of the equation is related to weather conditions. And so you can see that I had the temperature, dew point, visibility, wind speed, and then during each day the maximum temperature and the minimum temperature. And then there's these assumed values, and there's the vapor pressure of water, which is of course a function of temperature, and so I have it as a constant. Probably I'd have a little bit better model if I adjusted the vapor pressure of water in the atmosphere to vary as a function of temperature and relative humidity. But that's not a simple thing to do, so that's why I just selected a typical value. Net emissivity is talking about the reflectivity of the atmosphere, and it varies as a function of humidity. There's the ratio of how many of the daylight hours are bright sunshine versus cloudy, partially cloudy, and I just assumed half of the time is bright sunshine compared to cloudy conditions. And these were fine-tuned a little bit based on some other models that I saw people had constructed, and partly having to fit the data to try and find out what values would give us the best accuracy. If you right-click, then it is comments. So right-click on a cell, insert comment, and it's like a reminder, you know, of what equation you use or what it's meant to represent. There. To do that, let me show you with a fresh Excel. You go over here and that's not it. Well, they've maybe changed it. Used to be that you just drag, there's a little line over here that you drag down. I'm not sure how to break it now. I'll figure out how to do it in 2013, I'll let you know. In the old style, if you've got 2010, it's just you bring the cursor over here and you start dragging it down. insert. Uh-huh. Oh, yeah. Maybe. That might be another way to do it. Looks like maybe they've removed that. Oh, maybe, yeah. I'll figure out the new way to do it. I'll let you know, because that is a useful thing, because this is such a long spreadsheet. Sometimes I'd want to be looking at data from 2012, but I wouldn't want to lose my column headers, and so that's the reason why I had it split like that. So in the end, for every day, what I was able to do is calculate the potential evapotranspiration in terms of millimeters per day, and then I assumed that you couldn't have a negative potential evapotranspiration, and so I set those days equal to 0. And went through that process, and that's where the data comes from that shows, you know, this overall model quality. Now, you're not going to have to apply the evapotranspiration model for such a long period of time, and the model that you're going to use in the homework assignment is a lot simpler, in that you don't have to keep track of maybe such a detailed calculation of gamma or delta. But I am going to give you, in this homework assignment, a chance to sort of get your hands dirty in trying to predict evaporation. In the end, what I gave to the DEP as the best thing that they can use, the best tool they can use to predict how much water is available over the long term, is this chart that relates 7Q10. And that's a regulatory parameter that I wasn't familiar with until starting this project. And what it is in a 10-year period, what is the 7-day average that's the lowest? And so you'd look at every 7-day window during a 10-year period and find out what 7-day window has the lowest average flow, and then add 10% to it. And what I told them was, for example, if you are comfortable with not having enough water 90% of the time, then you can take out, looks like approximately 6,000 CFS. And so 10% of the time, 6,000 CFS is there. And you can still preserve the 7Q10 if they were extracting 6,000 CFS. The 50%, there's 1,000 CFS available for withdrawal, and you can still preserve the amount of water that's there for the 7Q10. And the 7Q10 amount, that's leaving that much in the stream, is basically for making sure that the fish eggs don't dry up and that there's some just minimal flow to try and prevent the stream from drying out completely. That's why they sort of leave that as the amount that they're not going to withdraw. And so basically any industry has its own tolerance for failure and for uncertainty. And if there's an industry that is willing to have their water supply not available 10% of the time, then they can count on withdrawing 100 CFS from this particular watershed. And 100 CFS, that's a lot of water, 100 cubic feet per second. And so it was an interesting project, and I learned a lot about evapotranspiration in the process. The main thing that I learned is just how complicated it is. And so I tried to pick out homework assignment problems for you that gave you a taste of that complexity but wasn't quite overwhelming. You can see that in part 1 of the assignment that I've given you, the first 2 problems are out of the textbook. Problem 7.1a is just like a watershed mass balance, not really calculating evapotranspiration separately, but more having to deal with the general model of watershed balance that I showed you here. There's a separate runoff model that's presented in that problem, and they tell you how much precipitation there is, they tell you how much a lake level increased, and they give you all the other parameters, and then you need to calculate how much evapotranspiration there was. during a certain period in that first problem. In the second problem, it's called the mass transfer evapotranspiration model, and it's not looking at the solar radiation yet. It's just strictly looking at atmospheric conditions and how much water could be removed from a system based on the atmospheric conditions. And then in part 2 is where I have you go get some solar radiation data and actually do your calculations on the combined model that takes both the atmospheric conditions and how much sunshine into account to try and predict evaporation. And so part 2 is probably a little bit more time-consuming than the first parts. Well, let's talk about some of the basics of evaporation. First of all, one of the driving forces in evaporation is how much humidity there is. And if we click on this link, it takes us to kind of an interesting definition of humidity, a really long explanation on the difference between relative humidity and dew point. You've probably heard of heat index before, and heat index is sort of akin to wind chill in that, you know, during the winter time, if it's cold and windy, then it feels colder than it actually is. And does anybody know why that is, by the way? Why is it that it feels colder on a windy day? I mean, it seems obvious, but why? I don't think it has to do with the water. It's moving air over you. You remember air is an insulator, and so when the air isn't moving, the heat that's radiating from your body can only radiate, the speed of the radiation is limited by how hot is the air that's next to it. And so right now, when I'm just sitting here not moving, my skin is warming up the air around my body. And that's why wearing a shirt, it feels warm, is because the shirt is trapping air next to my skin, and so the air isn't moving. But when it's windy, then the boundary layer, that part of the air that is warm around my hand, is much thinner. And so the heat can move a lot more quickly between my hand and the air next to the hand when the temperature gradient is a lot different. When there's a big difference between the air temperature and the hand temperature, then heat transfer is quick. But when there's a small difference between air temperature and hand temperature, then there's a very slow movement of the heat from one object to the other. So that's sort of why wind chill is accounted for during the wintertime. In the summertime, the reason why heat index is accounted for is because it feels hotter than usual. In this case, because remember, the way that we keep cool is by sweating. And if it's a very dry day and your sweat is evaporating quickly, then it feels cooler to you because you're losing heat through the vaporization of your sweat. You may remember from chemistry that, you know, it takes, not only does it take energy to increase the temperature of something, but it also takes energy for a phase change. And so it takes energy to take a solid ice into liquid ice, for example, and it also takes energy to move liquid water into the vapor phase. To evaporate water requires energy. And so on a very humid day, you may be sweating, but the sweat just isn't evaporating because the air is already dense with moisture, and so it feels like you can't cool off because your sweat is just dripping off of you and it's not having its intended effect of evaporation. You only get cool from sweat when the sweat evaporates, and then your body's heat is driving that evaporation, and so you lose temperature. And so this is showing in this, if you want to read through this article, it's pretty interesting but very long, talking about the relationship between dew point and relative humidity. And the main point that it makes is that when water vapor exists as a gas below 100 degrees Celsius, the reason why it does that is because it has enough kinetic energy to exist as a gas. Now, it's not that all water, you know, it's only above 100 degrees Celsius that water boils. But even when we are below 100 degrees Celsius, there is a vapor pressure that's positive. And you may remember from fluid mechanics that we took a look at a chart that had vapor pressure. I'm sorry, vapor pressure was on the y-axis. And increasing temperature was on the x-axis, and it showed that as temperature increases, vapor pressure increases dramatically. And then finally, the vapor pressure of water is 760 millimeters of mercury at 100 degrees Celsius. Well, water will still exist in the gas phase even when the temperature isn't all the way up to 100 degrees Celsius. And the reason for that is that some of the molecules have enough kinetic energy to exist as a gas. It's just not all of them do. That some fraction of the molecules that in a container of water have collided together. And the illustration when we were talking about vapor pressure is that the atmosphere is pushing down on the liquid, and if the water is cold, then there isn't very much vapor pressure. The water, because the molecules are bouncing together, there won't be very much movement of these molecules, and so a very small fraction of them are going to end up having enough sequential collisions to escape from the liquid phase out into the vapor phase. But if the temperature increases and there's lots of kinetic energy inside of the liquid, then we say the vapor pressure is high. And that's at the end of this chain of collisions, that when there's a high temperature and lots of collisions among the molecules, then a greater fraction of them are going to have enough kinetic energy to escape from that boundary of liquid and vapor. And so the process of high solar radiation is increasing the temperature of the liquid, and that accounts for why there's more evaporation on a really sunny day. It's partly related to the temperature and increasing the kinetic energy of the liquid for a certain temperature. And so here's just a look at what's happening at the molecular level during evaporation. We know that we describe how much gas there is above the liquid layer by relative humidity. The way that we measure the amount of water in the atmosphere is relative humidity. And what that's relative to is the total amount that could be in the air, so the saturation quantity. And so relative humidity is expressed in a percentage. The quantity of water molecules themselves can be measured as a partial pressure or in terms of the percent relative humidity. And the reason why the liquid water molecules vaporize is just because of the kinetic energy that the solution has. If you average over the entire Earth's surface, on average, there's 3 millimeters per day of evaporation. That takes into account the North Pole, the South Pole, the equator. Just the Earth's average is that there's 3 millimeters per day of evapotranspiration, taking into account free surface evaporation and also evaporation from plants and crops and things like that. And because water requires energy in order to vaporize, the latent heat of vaporization is what limits evaporation in a lot of cases. When the temperature is very low, there's going to be low evaporation because there simply isn't enough energy to drive the evaporation process. For example, the video we watched of pouring water onto a hot skillet, there is plenty of heat available for vaporization, and in fact the water is instantly vaporizing as quickly as it can get into contact with that hot pan. Solar radiation is the driving force behind evaporation. There's two parts that are both necessary for evaporation. The first thing is that you have to have transport, and the other is that you have to have energy. The combined evaporation model, which we'll get to eventually, takes both of those into account. So the first is that there has to be sufficient solar radiation or energy to drive the process of evaporation. And there's lots of different things that get measured when you download solar radiation data from a weather station. Sometimes the weather station will be measuring how much solar radiation is going to be coming into contact with the atmosphere. That's not measured so much as it's estimated. Then there are gauges that measure the amount of radiation that is going to be coming at a straight line. But then remember that sometimes the sun is at an angle, and so as the sun is starting to set, then some of the solar radiation is going to be reflected off of the atmosphere. Some of it's going to be coming at angles other than normal to the horizontal plane. There's also reflection by the surface of the Earth, and that's different from the radiation of energy from a heated surface. The net surface emission of long-wave radiation is how much radiation is emitted during the nighttime or when the surface is cooling, as the surface gives up heat that it is absorbed during a day-long period. You'll notice that if you add up all of the outgoing radiation values, that equals 100. And the reason why is that if outgoing radiation didn't equal incoming radiation, then that must mean there's an accumulation of radiation, or that the Earth is continually heating. And it may be continually heating a little bit because of global warming, but not at a very rapid rate. This is maybe looking on an annual basis. The energy balance method is looking at just how much energy is available to vaporize water. What's the latent heat of vaporization limiting? If you had some pan, or if you take an element of water, maybe this is just some certain part of a lake, and you want to keep track of the mass that's lost to evaporation. So m dot v here is meant to represent the mass of air that's lost due to evaporation. And so if you knew E, which is the evaporation rate in maybe millimeters per day, and you know the area of the surface and the density of the water, then you can come up with the mass flow rate of air due to vaporization. And what the energy balance method says is that you can keep track of the amount of volume inside of the control volume. So the change in the control volume multiplied, the change of liquid in the control volume multiplied by the density of water, that's accounting for the mass flow of the vapor. And then you also have to account for the velocity times the area. So if there is any moisture coming in through the control surface boundaries as well. The two terms here are storage and transport. And if you assume that this is like a pan that is impermeable, yeah?
Dr. Ware, is this similar to some of the equations, some of the math we studied in fluid mechanics?
Yeah, this should seem very familiar, like Reynolds transport theorem.
Yeah.
Yeah, Reynolds transport theorem had the same thing when we were doing control volumes and looking at in versus out in control volumes and looking at reservoir volumes increasing and decreasing. This is similar, yeah. Yeah, so CV means the same thing here as it did there. This is control volume, and CS stands for control surface. And the easiest thing to estimate evaporation on is a metal pan. Because out in nature, if you have a puddle and you want to find out how much is that puddle evaporating, it's hard because some of the moisture is going to be infiltrating down into the soil. And so, when you watch a puddle disappear that was a puddle in sand, you may not know how much of that evaporated and how much of it had infiltrated. So what we're saying here is, if we just want to isolate the evaporation, then let's assume that we have some metal pan and we're watching the water evaporate from a metal pan. And if you have a situation like that, then you can just simply know how much evaporation there is by looking at how quickly the volume drops inside of the pan. And I actually toyed with the idea of us doing an experiment of that. Like, I was going to bring in a metal cake pan and have each one of you fill it with a cup of water, and then everyone in the class would be assigned a different temperature to put their oven at. So maybe, Taylor would have 150 degrees, and maybe Chris would have 200 degrees, and you'd have to, with a stopwatch, sit there and watch the water evaporate. And I was it would be kind of interesting, right, to have a graph of evaporation time as a function of temperature, but I didn't have a cake pan handy, so that's the only reason why we're not doing that. Yeah. It's just the density of liquid water here. Because what you're saying is that if you watch the amount of water in here, and this is liquid, decrease, then that same mass flow rate is being lost as a liquid, as a vapor through the control surface boundary at the top. So you still use 1,000 kilograms per cubic meter as the density of water, because the V that's changing is liquid. But then the mass flow rate, it doesn't matter if it's liquid or if it's vapor, because you're doing it in terms of a mass flow rate. So maybe if I find a cake pan, we can do that series of experiments, and you'll have to sit in front of your oven with a stopwatch. But yeah, and then everybody has to make cake too. You can rearrange this storage term to try and solve for how quickly the water level is decreasing. And so, you know, we were talking earlier about a volume of water. There's a certain volume of water. Well, if you know the area of the pan and you know the depth of the water, then the changing depth over time will be able to tell you what is the vapor transfer rate out of the top of the pan surface here. So basically what it all simplifies down to is you can know the mass flow rate of vapor out of a pan if you know the density of water, the cross-sectional area of the pan, and then the evaporation rate, the E. So that's the liquid phase. Now the other thing that we have to be aware of is that we assume that there's steady conditions, and so that if this isn't changing over time, then the evaporation rate is partly limited by how quickly the water vapor can get moved away from the surface of the interface between the liquid and the air. Remember when we were talking about skin and how it's windy, it makes it feel cold because the heat is getting moved away from the skin more easily. If we have a free surface of water and there's evaporation happening, so this is water, then there's going to be like a layer very close to the water surface where it's very humid. And then there's going to be another boundary layer above that that's a little bit less humid. And then, that's an M. And then maybe we'll have dry air above that, you know, certain other levels, and so on, and then there's dry air. How quickly water can evaporate is partly a function of wind conditions, because on a very windy day, what it's going to do is it's going to make that layer a lot shorter so that the dry air is closer to the water. If the dry air is far away from the water and you've just got this fully humid layer of air above the water, then the evaporation rate is going to be limited by transport. But if it's a windy day and there's, you know, lots of turbulence and mixing, and you can get the air that is very low on moisture closer to the water surface, then that's going to increase the rate of transport from liquid phase into the air. And so the whole point behind this slide is just to illustrate that in addition to being limited by how quickly the water is evaporating from the pan, there's also the issue of how quickly can you get dry air over the liquid surface in order to move it away. We keep track of, in the energy balance method, the latent heat of vaporization, which is how much energy is required to vaporize a certain volume of water. And you can keep track of the mass flow rate to find out the total mass of air that's volatilizing and calculate the energy needed to volatilize all of that. And it's related to the radiation that's coming in, the emission of heat by the ground, and the emission of heat to the air by the water. The water is going to be giving up its heat to the air that it's touching and the ground that's beneath it. Radiation that is available for evaporation is partly related to the incoming solar radiation, but then there's also something that's called albedo, which is the reflection of the surface. And the way that you're able to calculate the net radiation is you've got the incoming radiation, the emitted radiation, and then the difference between the two is albedo. This equation is one part of the combined method when you take into account the radiation, the net radiation that's incoming and available for heating up the water, and then the latent heat of vaporization water, and then the mass density of the water itself. And the evaporation rate that you'll get from doing this will be in units of millimeters per day. We don't really have time to get into this series of examples, and so we're going to have to leave it here for today. Thursday when we get together in class, it'll be a lot more hands-on, and we'll go through a couple of examples that'll help you to get started on homework assignment. Before we finish for today, though, just remember that what you need to be doing right now for the project is trying to work on stage 3, which is translating both your surface data and the pipe data into getting it set up in StormCAD. And then once you've got that all set up and uploaded on the 31st, then we're going to talk about how to account for the actual wastewater flows that are in the combined sewer. So, all right, I'll see you on Thursday.